Okay, let's talk about imputation methods. So in general, I'm going to talk about a very general case where you have p variables in the data set, and you might have some complete cases, although it is not necessary for any of the methods that we are going to talk about that you don't have to have complete cases at all. So you could have missing values on at least one variable on everybody. So that's possibilities. And you have cases with missing values. So DOBS is the observed data, DMISS is the missing data, and Y can be discrete, continuous, or semi-continuous. Semi-continuous are the ones that have they kind of look like a continuous variable, but they have a spike at 0. So for example, alcohol consumption. So people who don't consume alcohol, they have a 0. And then people who have alcohol consumption, they have some continuous values. It's kind of a semi-continuous because then there's a big spike at 0. Same thing with the real estate income. So you have to have a real estate if you want to have a real estate income. Therefore, there will be a lot of people who don't have a real estate, their income will be 0, so spike at 0.
Gregor, you've got a question here in the chat.
Yeah.
Can you talk about this? So the question is, how do you decide whether you have a small or large data set? Can you just talk about that distinction?
Yeah, well, the asymptotic is sort of is not a very easy. So people ask me, what is your rule of thumb? So I always ask, I say, it's my thumb or your thumb? So yes, I think for the mean, for example, central limit theorems, when kind of a central limit theorem takes place, it takes into effect. Now, for the mean of the distribution, then it's really, I think, you can see the normal distribution taking place, central limit theorem taking place, even with the small sample size of 100 and 150 and 200 and so on. But on the other hand, if you're talking about the percentile of the distribution, and if you're talking about the tail area of the distribution, then the asymptotic arguments take a much longer, much larger, maybe in the ranges of 5,000 and 10,000 and 15,000, 50,000, so on and so forth. So this kind of it's a hard question to answer. But I think I would say is that because we have these methods available now for doing the multiple imputation, regardless of what the sample size is, but then you see the multiple imputation and maximum likelihood sort of kind of converge too. So I would say that the if I have a like a large, if I'm talking about the mean, if I have a 200, 300 sample size, then I can use maximum likelihood approach for that one. But if I'm talking about the tail area, I would require like thousands, and maybe if I'm talking about even a smaller tail area, then I might have to talk about even 10,000s of sample size. So it's not a satisfactory answer, but I'm thinking that that's kind of a ballpark number that I'm giving you.
That sounds good. Another one came in just now. I'm assuming this is referring to imputation methods. Which of these imputation methods would be most appropriate when we have a high fraction of missing data?
Now, the ones that I'm going to talk about is handles any kind of fraction of missing data. Now, this is another question people ask me too. Oh, I have a 75% of the cases are missing in this data set. What should I do? Should I do imputation or not? I always ask them, what's the alternative? What are you thinking of doing? If you're dropping that variable from the analysis itself, then you're changing the research question. So that variable is no longer relevant for your analysis. Therefore, that's not a missing data problem for you now, because you're you're omitting that variable. But if you say, no, that's very, very important variable, I have to include them in my analysis, then I would say is that imputation method is the best way to deal with that problem, depending upon how many covariates you have in order to compensate for that missing values. And he says, oh, no, I don't feel comfortable imputing 75% of the values. Therefore, I will just analyze 25% of the data. That's even more biased, right? So this question is that the imputation method I'm going to talk about is generally valid for any fraction of missing values. A key is that whether or not you have good covariates to predict those missing values. And that's the key question, is that how do you incorporate as many covariates as possible to really compensate for the variables with missing values? Does that answer the question? Sort of indirect way.
Yeah, I think so. Yeah. Thank you.
Okay. So the setting, we are going to talk about multiple users analyzing different subsets of variables. So here is it's kind of a context of, ISR here, because we produce all these big data sets, and different people are using different subsets of the variables. And we are going to use multiple analytical techniques. So some will be just descriptive. Some will be just linear regression. Some will be complex latent variable analysis. And there are different skill levels dealing with incomplete data. So we don't want to bother them with dealing with this incomplete data. Analysis to be performed with a complete data set is known. So you know exactly what you would do if you had no missing values. And software to perform complete data analysis is available. Some want to use Stata, some want to use M+, some want to use SAS, SPSS, and so on. What about software to perform complete data analysis? And we're going to assume missing at random. So that is conditional on observed characteristics. The residual difference between those with missing and those with no missing values are random. That is within the block created by the observed characteristics, the differences between the respondents and non-respondents on the variable is random. Now, if you're not willing to make that assumption that they are random, that is, if you are wanting to know it's missing not at random, then it is your responsibility to say, okay, how different they are. And you don't have any data for that. So you have to really do some sort of a sensitivity analysis. Okay, what if they were different by 10%, different by 20%, different by 30%? So the technique that we were talking about, or I would be encouraging you to think about, do the imputations under missing at random, and then perturb them, shift them by certain percentages, and see how different your inferences are with that perturbed data set. And in my book, I talk about these kinds of strategies, and I give you several examples about what is called a sensitivity analysis. Is that let us alter the imputed values and see how different the inferences can be. If the inferences are very similar, that means that your inferences are robust, in the sense that it's not sensitive to your assumptions about missing at random. So if you think that it's missing not at random, I would encourage you to do some sort of a sensitivity analysis, and those kinds of examples are described in my book, as well as in Little and Rubin's book. So the imputation is to fill in those missing values. Goal is good inferences for parameters or population quantities, but not the best estimates of the missing values or the true values of the missing values. So I remember, I think, years ago, when the multiple imputation was still a very in the infancy, and I gave a presentation about the room full of MDs and about the missing imputing values and so on and so forth. All their jaw dropped. Said, "What? You're making up data? How can that be true? How can that be right?" I told them, I said, "No, I think our goal is to get good inferences and parameters of population quantities, and you're trying to estimate." They said, no, it can't be right. We'll give you a test. So we are going to give you a data set and hide some values, and you do imputation. I said, okay, good. I'll do imputation, and then they said, okay, now I did the imputation as best as I could, and went back. And then they said, okay, what did you get for ID number 1357? And it was some income. So I said, oh, 15,000. They all smiled. They said, wrong. That value that we actually deleted was 30,000. Okay, we'll give you another chance. What did you get for ID numbers 14782? I said, I got 30,000. And they smiled. They said, wrong. That guy is 15,000. So then I realized what they were thinking, that by this doing imputation, I will do some sort of a magic that they will actually get the true value of that variable. I said that if I could do that, I would be living on the penthouse and not giving you lectures, but you all will be coming and visiting me. Right? So the idea is not to get the best values for those imputations. Imputations are not real values. You are never going to get the actual value that respondents should have given you through this imputation. But what you are doing with the imputation is that you are getting a plausible data set from the population. Therefore, the inference is plausible inference. And in the process, you want to make sure that you have an incorporated uncertainty associated with the imputations. Knowing well that imputations are not real values. That's the whole goal, is about the inference about the population, not about inference about the individual. So therefore, the imputations have no microeconomic or micro interpretation, micro data interpretation, but it's only in the context of aggregates, in the context of test statistics or estimates and so on. And they are really giving you inference about the population that you intend to draw from. Now, the central theme of accomplishing this is to make sure that the imputations are draws from some sort of a predictive distribution of the missing values given the observed values. So imputations have to be sort of a draws rather than plug in the estimate or value. So the features of the imputations is that you get a rectangular file, you are retaining the observed data, and you are handling the missing data once. And once you have done the multiple imputed data that you give out the data set, then you are done with the missing data. Users don't have to worry about the imputations. And it exploits the incomplete cases. Now, the bad features is that naive methods can be bad. Sometimes I think I talked about mean imputation, last observation carried forward, that your unrealistic assumptions, and therefore you could be those naive methods can really be bad, and invents the data in the sense that you can't treat these red values as true values. They are not true values. Therefore, you have to, if you don't incorporate the uncertainty, then you are understating the uncertainty. So you have to incorporate some sort of a uncertainty associated, or kind of increasing the standard error to reflect the uncertainty about these imputed values. Now, imputing means I talked about is here's an example where you have two variables, y1 and y2, and the data are missing at random. That means missing values of y2 can depend upon y1. But unconditional mean is that you just plug in the mean y bar 2. So what's the problem with that? Now, if you look at this as a plausible data set, then all the imputed values are sitting on that horizontal line, y bar 2. And it's not a plausible data set from the population, because the plausible data set should have the scatter around y1 and y2. And therefore, the unconditional mean imputation is not a plausible data set. The other problem is that, suppose say the mean of y2 is y bar 2. That's good. What about the standard deviations of y2? Now, standard deviation of y2 is underestimated because the y bar 2, because they're sitting on the right on the mean, they don't have any contributions to the sum of squares. Therefore, the mean, that standard deviation, but you are dividing it by n-1, but the numerator is 0. Therefore, you are underestimating the standard deviation. And you might say, well, let us do conditional regression imputation. So you take the fit a regression model of y2 on y1, and then you predict from the regression model, then you plug in the regression estimates. Now, by far, these are the best estimates of the missing values. But then it is not a plausible data set, because you have a bunch of people sitting exactly on the line. I have never seen any data set where you have a y1, y2 scatter where a bunch of people are sitting exactly on the line, and that all the imputed people are sitting exactly on the line. Therefore, it's not a plausible data set. Now, it is better than unconditional mean, but then you are underestimating the residual standard deviation around the line, because these people who are sitting exactly on the line are not giving any contribution to the residual variance, but you are accounting for in the denominator, you're accounting for the number of cases to be n, and therefore you are underestimating the residual variation. So conditional is better than unconditional, but still it has a problem that it is not creating a plausible data set. Therefore, it underestimates the standard deviation to a lesser extent than the unconditional mean, but still it is underestimating the standard deviation. So the properties of these mean imputations, the marginal distributions, associations estimated from the filled-in data are all distorted. The standard error of estimates from the filled-in data are too small because the standard deviations are underestimated, but also sample size is overstated. So you really have to incorporate that fact that the sample size is overstated when you just analyze the imputed data without accounting for the fact that some of them are imputed values. Conditional is better than unconditional mean, which can be worse than the complete cases, because you are filling in the data with such a drastically reduced variation that all kinds of regression coefficients, everything is all kind of affected by these filling in data. So the imputing draws kind of reflects that uncertainty in that regression relationship between y1 and y2. So ideally, picture, schematically, this is the way you want to think about it. Suppose you draw a scatter plot of y1 versus y2, and the red dots are imputed values, blue dots are missing the observed values. Now, if I look at the picture, if it is a plausible data set, then for the entire scatter, blue dots and red dots should be sort of exchangeable. They're kind of interspersed, randomly interspersed. That's the kind of plausible data set from the population. So that's the kind of intuition that we want to make sure that the randomness in the observed data is also reflected in the imputed data, so that combined observed and imputed data look like a plausible data set from the population. And that's the goal of creating this imputation. And then draws are the way to create that imputation. So here I would take the predicted values and then add a residual. Now, for example, if I'm making the normality assumption, and then I can draw the residuals from a distribution with mean 0 and variance, residual variance estimated from the complete cases. Or if I can be non-parametric, then I can say that, well, let us randomly select a complete case residual and then add to residual from the predicted to the predicted values for the non-respondent. So either you can use a normal distribution based random draw, or you can do a non-parametric draw from a non-parametric distribution of the residual. Now, if you are talking about the binary data, then you have the predicted value. For example, you run a logistic regression, you get a predicted value for the probability of yi2 being 1. Then you just draw a 1 or a 0 with the predicted probability pi2 hat, and 0 if it is 1 minus pi2 hat. That is, you draw a uniform random number, and if a uniform random number is less than pi2 hat, then you put it as a 1. If it is greater than pi2 hat, then you put it as 0. So that's a way of setting the value, imputed values, to be 1 or 0. Now, these methods are called sort of not a proper, because in the context, I'm estimating the model. Therefore, there's an uncertainty in the estimated model. So the proper way of doing that is to incorporate the uncertainty in the estimate of the model parameters and then draw from that. So it's kind of doing it in a more Bayesian way is a proper approach. That's what we'll be doing in most of the examples of the software packages that we'll be talking about. So the properties of imputed draws is that it adds a noise. It might, well, it's kind of you want a best estimate of the missing value, but you are adding a noise to it. It may appear to be less efficient than imputing means, but there's no bias for estimating distributions now, because now the scatter looks like a plausible scatter from an actual sample that you could have observed, or from a plausible sample that you have observed. Therefore, the distributions are all estimated. Now, this point is also important that the more robust nonlinear transformation. Suppose, say, there is some nonlinearity in your relationship between y1 and y2, but you fitted a linear model from that. But because you're adding a noise, then that means that it kind of gives you a protection for the nonlinearity. And so it's kind of you're getting a benefit of being model being misspecified, but if it is if it's slightly misspecified, if it is really misspecified, then you don't get that much of benefit, because that adding a noise is not a compensation for really bad model. So it's very, very important that you do the analysis properly, in a sense that make sure that the model fits the data well when you are doing the imputation. So conditional draws is better than unconditional, but improves the efficiency. It preserves the association with the condition variable. So you want to really make sure that the standard deviations are okay, but the one problem that we need to solve next is the sample size is overstated, and that's where the multiple imputation will fix this problem.
Raghu, can I jump in with a question real quick?
Yeah.
This is you just touched on this in your last slide. So the question is, can users use general multiply imputed data sets for nonlinear models such as survival analysis? So can you just talk about kind of the limitations, if there are any, with what sort of analyses you can do on the back end with a multiply imputed data set?
Yeah, well, pretty much I think from my perspective, if the good set of models have been used to derive imputations by using kind of a good diagnostics and so on, practically any method can be used. So in the survival analysis context, so suppose say you're missing some covariate data and you fit a good fitting model for that predicting that covariate data based on whatever the information that is available, including the survival times and censoring indicator. Then you can use that imputed data to analyze any nonlinear model. So the problem comes in when you are when you didn't do a good job of fitting, trying to get a good model to fit the data and then do the imputation. So for example, in this case, it's a highly nonlinear data. And any scatter plot of y1 and y2 would tell you that it's a nonlinear data. But you just said, well, I don't know, it's too hard. Let me just plug it into IVWare, which assumes linearity. Let's plug it in and get the data out. Of course, that data is going to tilt you towards the linearity because the imputed values are assuming linearity and the observed values have nonlinearity. So you have now biased the results towards the linearity, so you may not be able to detect that nonlinearity. So it's not about whether or not imputations can be used for linear or nonlinear model. It is really whether or not the imputation models that you have generated reflect all the structures in the observed data set based on which you're doing the imputation. Does that make sense?
Yeah, that's a great answer. Thank you.
So whether you impute conditional means or draws, you know, in the nowadays, I think in the machine learning literature, a lot of imputations are done, but they're getting impute conditional means to get best estimate of the missing values. This is very common in machine learning literature. But if you want to get valid inferences, not the estimates, valid inferences, then you're better off imputing conditional draws. And valid standard errors can be obtained by multiple imputation. That's the focus of this workshop, right? So in a machine learning literature, it's a kind of a hard thing to do because it's kind of everything geared towards an algorithm. And how do you incorporate the uncertainty in that algorithm is still an open course. Any questions so far? Now, this is a common question we ask. I am interested in regression analysis. What should imputation condition on? Should be observed covariates and outcome if imputing draws. Observed covariates only if you are imputing means, that conditional means. Now, sometimes you are not interested in the standard errors. So there are some situations where you are not really interested in standard errors. You're really interested in getting means right or estimates right. In that case, imputing draws may not be that important, right? I'm not even computing standard errors. I'm just computing the estimates, and then that's all I'm going to be concentrating on. I don't know. As a statistician, I won't do that because I don't think there's any meaning to estimates without knowing what the uncertainty associated with that estimate is. So if you're really only interested in estimates, then probably imputing means using covariates alone is okay. But imputing conditional means can be less efficient than complete case analysis unless the imputed case are downweighted. So if you do an imputation conditional mean and then pretend, it can be less efficient than the complete case analysis. So there's a nice paper by Little in 1992 that talks about missing data in regression, an overview, and talks about these kinds of issues. So from a practical perspective, I normally recommend that you just do the imputations using draws. And that covers almost everything that you want to do, point estimates as well as good standard errors. Now, this problem comes in often. Maybe I think we can take a break after this. Should imputations be conditional on all observed variables? Now, in regression analysis, people get hung up on this dependent and independent variable. So let me take an example in the context of consumer expenditure survey, which is conducted by Bureau of Labor Statistics. And they have a lot of missing values in input income. But they have very little missing values on expenditure. So it's interesting is that people don't mind talking about how much they spend on various things, but they're very reluctant to talk about how much they make. So income has a lot of missing values. Expenditure has very little missing values. So substantive models that they're really interested in are the relationship between income and expenditure, or expenditure and income. So sometimes they use expenditure as a dependent variable and income as the independent variable. Sometimes they use income as the dependent variable, expenditure as the independent variable, and so on. So one of the things that they were really concerned about, that using the expenditure to impute income and then putting the income in the regression model. It's kind of double dipping. That is, hey, you have already used expenditure to impute income, and then you are putting the imputed income in the regression analysis. You're using twice somehow, and doesn't it create sort of a endogeneity problem, right? right? So this endogeneity problem creates a hang-up on lots of people. Should I use the right-hand side variable or left-hand side variable in imputing right-hand side variable, and right-hand side variable imputing the left-hand side variable, because somehow that mixes up. Now, my answer would be, of course, you should use expenditure to impute income, and you use income to impute expenditure. Why not? Why not? Because income has to give information about expenditure, and expenditure has to give information about income. So the imputation should really use all the information that is available on that individual. And BLS researchers were not convinced. Said, no, I don't think so. Well, let's do a simulation study. So they created a population by accumulating complete cases over several years. And they drew 200 random samples of size 500 each. These are called before deletion data sets. Then they secretly created missing data on the outcome in each data set and supplied the 200 data sets along with 55 covariates to me, the University of Michigan. And I did not know, UM did not know how income values were deleted, except that some or all of these 55 covariates were used in specifying the missing data mechanism. So I don't know, that's a reality, right? The 55 covariates, all I care about is that it's missing at random, in the sense that it's conditional on the 55 covariates. The observed and missing values are random, but I don't know which covariate and which subject, which covariate were used. So that's a reality. I will never know what the mechanism actually is. So UM created two sets of imputations, using expenditure, not using expenditure. So impute the income. So imputations were created by drawing values from the posterior predictive distribution of income under an explicit model. And I used cube root transformation for the income and developed the model. I did all good diagnostics, and I satisfied that it was a good fitting model. Only difference was one included expenditure as the covariate or the conditioning variable, and other did not. And then the two sets of imputations, imputed data sets, and then actual data set. The actual data set, the before deletion data set, is still with BLS. So they did not send the before deletion data set to me, because if they had sent it, then they were suspecting that I might sneak into it. And so they didn't want to send that data set. So they analyzed the data set, that BLS actual data set, the before deletion data set. I analyzed these two sets of imputed data set. One included expenditure, the other included the variant. Other it did not include. So the BLS models of interest is to regress the food at home expenditure on income and some covariates. So beta 1 is of interest in this model. Here income is being used as a covariate, and food at home expenditure is used as the left-hand side variable. The other one was the Tobit model, which is the food away from home as a outcome variable, and then the income and some other covariates as predictors. So here gamma 1 is of interest, and these are left-censored values, in the sense that you have to be working away from home in order to have a food away from home expenditure. So these are kind of a Tobit model, it's a left-censored values model. So here is the two scatter plots. So you have the actual data set estimates on the y-axis, that is the BLS produced on the actual data set, the 200 before deletion data set. And then you have the imputed data set on the x-axis. So one imputation, one excludes expenditure and one includes the expenditure. So the graph on the right includes the expenditure in the model. Now you can see that actual data estimates are much larger than the imputed data estimates in the left-hand side panel, which excludes the expenditure. Whereas the scatter is around the 45-degree line and when you include the expenditure in the model. The reason is obvious, right? So if you don't include expenditure in the model for imputation, that means among the imputed values, you are assuming zero correlation or zero partial correlation, conditioning on the covariates. So the imputed values are going to be biased towards the null. So that's why in the imputation process, you want to make sure that you are conditioning on every variable that is available in order to maintain all the relationships in the data set. So the imputation process, by including the expenditure, maintains the relationship that is observed in the data in imputed values as well. And that's why you really have to condition on all the covariates and in any regression analysis, as many covariates as possible. So same thing, you can see that in the Tobit model, is that actual data estimates when you exclude the expenditures are much larger than in the imputed data set when you exclude the expenditure. And the scatter is around 45-degree line if you include expenditure in the model. So what should imputation condition on? In principle, all observed values, whether it's a predictor or outcomes of the final analysis model. It may be impractical for a lot of variables. That's why you may want to do some sort of a variable selection because you apply similar ideas. But for example, when you do weighting, you want to really focus on the variables that are correlated with both response, non-response, as well as the variables, survey variables of interest. So the priority to be variables that are predictive of missing variables, and then also non-response. And we will favor on the inclusion side than the exclusion side. So for example, we would like to make sure that we are building the model as big a model as possible, so that as more conditioning as possible, as much. Okay, let's take a break at this point. Is that okay to take a break?
There are a couple questions in the chat. You may want to, before, I mean, it's up to you if you want to do them now or.
Yeah, let's do it now.
Okay, so I'll just take them in order. So the first one says, I'm not quite sure I understand this one, but talking from social science viewpoint, should we be more interested in having reliable estimates of the distribution or of the parameter? In other words, should we rely more on the mean approach than the draws approach? That's the question.
Yes, so actually reliable estimate of the distribution or the sampling distribution of the parameter estimate, right? So you really want to get the inference right. So if you're from a social science viewpoint, you are really wanting to standard error estimates have to be right. So sampling distribution estimates have to be right. Therefore, you have to do draws if you want to get the inferences right, confidence interval to be right, p-values to be right, standard errors have to be right. I've never seen a social science that says that, well, I don't care about standard error. No, you do care about standard error. You do care about confidence interval. So therefore, we should be relying more on draws rather than the mean.
Okay, I think you got that one addressed. This next question is about two-arm randomized control trial. This person says, if data were collected from a two-arm randomized control trial, not an observational study, would your recommendation differ? For example, if we have treatment at time 0 and a health outcome measured at month 1, 2, and 3, to what extent would it matter which of these variables is utilized as a dependent variable and independent variable in the imputation model? The data and analysis model would respect the time ordering of the treatment indicator at time 0 and health outcome measured at month 1, 2, and 3. It's a little bit complicated question, but let me know if you want me to read that again. But
No, I'm reading it now. I'm seeing that in the chat also. So
good.
Yes, I think in a longitudinal analysis, if I have information, if I'm missing information in wave 1, but I have information from wave 2, I would definitely use wave 2 to impute wave 1. If not, then I'm making this assumption that wave 2 has nothing to do with wave 1. Now, practical matter is that when you are doing the imputation, sometimes in a longitudinal study, that you are doing the imputations for the wave 1, releasing the data. And then you come wave 2, and then you see some people who were non-respondent in wave 1, but respondent in wave 2. No, you don't normally go back and re-impute them. That's from the logistic perspective, because you've already released the data set of the wave 1, and you don't want to go back and re-impute the wave 1. Otherwise, if I take the PSID, then they'll be going back and every year, and then it'll be going back and re-imputing the values. So from a practical perspective, from a logistic perspective, that they don't want to re-impute those values. So from the point of view of seeing this as a one data set, if I'm analyzing it as a one data set, I would certainly impute the missing values, all the missing values, regardless of whether it's the outcome variable or the predictor variable. Now when I'm doing the analysis, I might ignore the imputed values in the outcome variable, because that doesn't add much any information at all, unless there are auxiliary information that have been used to impute the missing outcome variable, or missing dependent variable. So it all depends upon that what auxiliary variables that you have in carrying out the imputation process, and therefore the analysis is completely different than the imputation. The imputation is to exploit the full scope of information that is there on each individual to predict what you don't have. It makes sense?
Yeah, I think so. And obviously this question's from Jamie Yap. I mean, obviously, Jamie, if you want to follow up, please feel free to do that. Next question is, how about the outcome variable? Should that be imputed as well?
Now, let me answer that question. Suppose, say you have an outcome variable y, and you have, that's the only thing that's missing. And you have covariates that are all completely observed, right? Then there is no benefit, and it's missing at random. Then there is no benefit in imputing the outcome variable, right? Let me see whether I can share this. Let me share. See whether I can write this thing. So you have a y variable here, And that's missing for these people. And you have an X variable, and that is observed for all. Now, under the missing at random assumptions, f of y given x for a respondent is exactly same as f of y given x for the non-respondent. Therefore, these people don't have any information about the regression relationship between y and x. So the entire regression relationship is between y and x is coming from the respondents. In this case, you can do a complete case analysis that is valid under missing at random assumption. Now, on the other hand, suppose you have a situation where you have y and you have x1 and x2, and you have situation where you have observed, and then you have a observed, missing, observed, and then you have a missing, observed, missing, something like that. So missing, observed, so on and so forth. So you could have different kinds of missing data problems. In this case, you want to do all imputations using y, x1, and x2. So you want to do the imputation using all of them. After you've done the imputation, then you might say that ignore the imputed y's. Because the y's are useful only to the extent that they are useful in predicting the missing x1 and x2. And once they have done that job, then there's no relationship, there's no information about the relationship between y and x1, x2, other than what is there in the observed data set, observed values of y1. So depending upon in what situation you are, then you want to impute it, then you want to ignore it. Now let me take another example. You have a y, x1, x2. And y is supposed to be a self-reported income. And these x1, x2 are covariate. But you have a z, which is the administrative admin record income. And then there are no missing values here. There are some missing values here. And there are suppose some missing values here too. In this case, you're better off doing the imputation of the income, self-reported income, and then using the self-reported income imputed values in your ultimate analysis. Why? Because this gives you the information about y, which is incorporated in the imputation process. So in this case, your imputed income is better because it incorporates the information from the auxiliary variable about that income. So for example, the CPS income, and then this is the Z is the tax record income. So if somebody were to do the imputation using the tax record income, you are better off using that imputed income in your as a dependent variable. So the question is really depends upon which kind of situations you are in.
Okay, great. And then we've got one last one. What if we have a specific exposure of interest and we want to observe its impact on the outcome? I understand that including the outcome in the imputation of this exposure or vice versa will improve the imputation accuracy, but are we at all concerned about inducing a correlation between the two variables? Simply put, what happens if we use A to impute B to observe, and then to observe the relationship between A and B later? So
exactly, that's a consumer expenditure example we were talking about, right? So if you don't include A to impute B or B to impute A, in your imputation model, you're assuming zero correlation. That will automatically bias it towards a null. Therefore, in the imputation process, don't worry about whether it's income, whether it's a dependent variable or independent variable. Just do a good job of predicting the missing values using all the observed values on that individual. Whether it is longitudinal, whether it is dependent, independent variable, so on and so forth. So therefore, I like to think of imputation as a process by which I am trying to rectangularize the observed data in a best possible manner, utilizing all the information that is available in the data, exploiting all the structures in the data. Once I have done a good job of doing the imputation, then I can then decide about the analysis. How do you do the analysis? Right? So don't get caught up on this dependent, independent variables when you're doing imputation. If you get caught up, then I think you make these assumptions about that. In the BLS example, is that if you don't include the expenditure, you get biased results. Why? Because you are imputing zero correlation. So if you're imputing zero correlation, therefore you're going to get biased results. So you want to impute whatever correlation is there in the data set is to be reflected in the correlation in the imputed values. That's a critical.
Great. So I think we're all clear on chat questions. So I think we're clear to take a break now if you want to do that now. Or
okay, let's take a 10-minute break. No, let's come back at 11 o'clock. 10:51 for me. 11 o'clock?
Yeah, that sounds great. So yeah, let's break till for 10 minutes, like you said, and we'll be back here at 11 o'clock Eastern.
Okay, good.